This is an
Hey.
impromptu session whereby I am sleep deprived and I am going to ask Voz to explain to me how dynamo guards work. And then we're going to talk about Voz's recent PR, which changes some details about how we do guards on buffers for dynamic shapes.
Mhm.
Okay, so my question before we decided we were going to live stream this was essentially how exactly does doesn't guard normally work? Because Voz was telling me about how tensor match guards are different.
Mhm.
So
Uh,
okay, so type match seems like a pretty reasonable guard. So type match basically just says, hey, you had this variable and it needs to be this type the next time around. Otherwise, we're going to invalidate Dynamo's cache. So what exactly is this code doing?
yeah, so let's see style work inside out. Let's look at what check type ID is because that's sort of at the
No,
center
that's
of.
fine. Check type ID is just a function that given a type and a object checks that the type of the object matches the ID, right?
Mhm.
Like
Yes, but
it's the C implementation is trivial.
well, the implementation is trivial, but most importantly is that it's a trampoline. It references a C function, which
Yeah.
is what a lot of our guards do. Because if you remember, like it's important to think about the life cycle of the guards in that they're called at frame evaluation time. So you're calling them the next time you encounter this frame, which is why it's worth bringing up that these functions should be callable from anywhere.
Yeah,
Um,
this makes sense because we're generating a piece of code that will get run later when we're trying to check if the guard is valid or not.
Well, we've had bugs where we do like torch.equal in a guard, and you can't do that because it might not have PyTorch there.
We might not have PyTorch. Oh yeah, and yeah, so all the code has to be written in a way that we can, what are we're not evaling, we're execing the code or something with a closure environment, giving us binding all the identifiers.
Mhm.
Yeah, so okay, that makes sense.
Yeah.
Uh,
And there is an object called the guard. We'll get to that in a second. It's
yeah, I don't. This object always gives me trouble. So
well,
like,
there's guard builder, there's guard source, and I think guard source is a little bit different from source. There's like a little bit of nuance around some of these things. Most importantly, so type match these uppercase ones, you'll find them also in create fns, which we'll get to, but you'll see them called like this: guard builder dot type match. And the most interesting thing is, although they are instance methods,
we
um,
don't actually call them. They get called later
you get called
somehow.
later during guard dot create. Um, so there's a def create here that will actually call these
Okay,
things.
let me ask the question. So the dumb question is, why don't we just call the guard functions while we're creating the guard? Wouldn't that be the normal thing to do?
Well, I mean, there's like three layers here, right? There's like three sort of lifetime notions here. There's uh, the first one, which is when you're calling it like all caps, not actually invoking the instance guard builder dot type match. That's the guard accumulation. Then the guard installation is when it gets written to checkfn, and then there's actually calling it, which is the code produced from def type match, for example. And so I think you're asking not why don't we call check type ID? I
No,
think
I'm not asking about calling shape. Obviously, that has to be run when we're actually evaluating the guard. What I mean is, why don't we just code gen everything immediately when we're prior to guard installation? So you said there were two steps before checking. It was guard creation and guard installation. Yeah, so I
yeah.
don't understand why there's two steps there.
There's a couple of things. One, not all guards that are created get installed. Um,
Right. So this is the thing that I've mentioned on my architecture of Dynamo doc, which is
mhm.
that guards are sort of lazy. So we'll prophylactically create a guard for a value, but then we if you don't actually end up using it in a way that matters for the like final generated bytecode or FX graph, then we just don't actually guard in that case. So that's one reason, right?
Yeah, the other reason is that it's not cheap to make them because you're going to be just like putting together a bunch of strings and doing a bunch of
Okay,
uh,
so right, so because I was like, oh well, can't you just construct the strings and then later you just you throw out the strings you don't need? Okay, so avoiding a bunch of string formatting that seems legitimate. So okay, so I'm just gonna think of these as like lazily evaluated functions where like eventually we actually call them if they're needed,
Yeah,
because I'm a rabid Haskellr, and that's what
yeah.
Haskell's all about.
Yeah. So that's a great mental model for it. So if we look at where, so now we know
No,
we
but wait, it's not complete because normally funcs don't take arguments, but this takes an argument. So I guess the guard is just the like closed over variables from the context or
well, think
whatever.
of accumulating as you're accumulating like, for lack of a better word, promises that then go and get executed later once you do have the values. So if we look at def create, which is where this happens, and we look at create fn. Remember how we talked about create fn getting installed? This create fn is that callable. If we were to unpack the guard, create fn would be type match for some, ID match for others, tensor ref for others, and so create fn is, and it's kind of annoying because create fn is stored on the guard, but is also then called with the guard, and so it like feeds it to itself. So is self here is a guard. And so you do guard dot create self dot guard dot create fn, and it's going to take self as one of its arguments because that is that same guard that's passed in. And you might wonder, well, wait a minute, why is self like on here and on here? It's because the guards, the callables in create fn actually belong to the guard builder. Their identity is a little bit different. And so for simplicity's sake, or maybe for insanity's sake, I don't know, maybe I've been staring at this too long, it all makes sense, unfortunately. But this self here is the same as in this guard in def type match.
Also, hi proponent, thanks for joining us on the stream. Always nice to have people pop in. Feel free to ask any more questions you might have. Okay, type match. All right. So there's some business with the guard builder and the guard. Actually, sorry, if this doesn't matter, we can skip it. But didn't we pass two arguments to guard creation function? But now there's only one. Now there's only one argument at the actual create
Yeah,
func.
so this is just a way to get it back. This is a way to get back the so let's create a fan. Let's see where create a fan is bound. Um
It's guard builder, right? And we're looking at guard builder right now.
yeah, there's like a layer of indirection there that is kind of annoying. So guard is a data class, so we can look at where the guard is constructed. And this fn comes from make guard. Source gets make guard called on it.
Wait, don't we just want to look at the all caps methods on guard builder? Isn't that what I was asking about?
Yeah, but I wanted to show you the function as to how it makes it all the way through to there because you're calling make guard, if that makes sense.
I'm calling make guard.
Yeah. So let's
I'm
find
indirectly calling make guard.
well,
Oh,
make guard on source is what ultimately constructs a guard, which is where the callable is assigned from. So I was just showing you how it gets routed through here.
yeah. I mean that seems fine.
Well, I think it's worth seeing what fn is, what that is, so you can see what that first argument is. It's not replace guards. Yes.
Tell
So
me
this
what I'm looking at. Yeah.
So this is the same function. I'm just walking through how it gets passed in. And so def make guard takes this fn, then this fn is stored on the guard as the third arg. We go to guards. This is this create fn. And so your question was, what is that other argument?
Yeah.
Yeah, so def match, that is for self. Because when you're storing that callable, even though it has the identity, you don't like, from what I understand with
No,
Python.
but aren't these methods? They're not methods.
What's, I mean, versus functions? Is that what you're asking?
Well, like normally, if I call a method on an object, I don't have to pass self explicitly, right?
No, you do. You do with methods. You don't with functions, from what I understand. Right? Like if I have like let me just like do a weird thing here. Class foo, and I have like def x. So, and
Oh, are
then
you telling me that we didn't actually construct foo when we grabbed x off of it?
yeah, and then so
That's so confused. Why did you call it self?
yeah, for lack of a better word, uh, it makes
That's
it feel like
terrible
makes
because
it
it
feel
gives you
funky.
totally the wrong idea about how the method's being used. Normally, you would construct the object and then call the method on it, and then the self field would be populated. But okay, this makes more sense now.
So
So
I actually I will defend self here. I will defend self here for two reasons. One, it feels more organic because you actually shouldn't when you're like you do have an instance of a thing and it does have a selfie identity, and we do contractually promise that it will be a guard builder. And like when and then you also sometimes call these from other ones. And so there is some value in saying, ID match will call self.type match. I think
yeah, this is the normal way to call it. That this
but,
makes
but this
sense.
self is also the cursed self that you don't like. This is that one.
I mean, cause we started off cursed, and then we cursed all our descendants
Yeah,
forever and
but
ever.
this is that. But for lack of you can call it whatever you want. It still plays that same selfie role, which is like, hey, here's the instance that we are invoking these on and potentially storing some state on here. So just to walk through where we were,
Okay, so we construct a guard builder and then
Mhm,
we just call the function directly because the functions are not bound. Because indeed,
mhm.
we don't have the guard builder at the time we are like initially
Yeah,
constructing these things. So we can't even create a bound method. So we do have to bind it later.
yeah, and it's guard builder, not parentheses. This is just guard builder of the class.
Okay,
Yeah.
so somewhere there's a guard object. Make guards, I guess, makes the guard object.
Guard in source is where we have in well the symbolic shape expression is the one exception to it because that whole thing is full
Yeah, yeah, yeah. But yeah, make guard makes a guard, and it also puts in your function and a bunch of
of
useful info. And so this essentially is morally a closure, and we're going to call it later. No, we still have to make the guard builder, but once we have the guard builder, then we are ready to actually execute the body of this guard.
yep. And if we look at where create guard is called, what was it? It wasn't create guard, it's make guard. F create. Oh, just F create. So if we look at where dot, create is such an overloaded word in Dynamo. Everything is
Oh.
create.
You know what's so horrible? You call self.create fun, and so you think, oh, it's a method call in self. Wouldn't that be the normal thing to do? But no, you're projecting out the function from self and then calling it. And by the way, that function looks like a method, but actually it's not getting. I'll probably submit a PR to like factor that into assign out the function and then call the function. That would make a lot more sense.
That's fine. That doesn't sound unreasonable. So this is where we call create. This is where we actually take the accumulated guards and install them. Create takes a local builder and global builder because these are references to scope, for lack of a better word. And the
Yeah, I also like kind of don't understand this, but I also want to skip this because we haven't even gotten tensor match yet. So
yeah.
you can assign this with me another day,
Okay,
unless you
so
think it's important.
not that important. But the most important thing is when you call create here, you are writing things to the global local builder that you can think of it as like an intermediary object slash context that compile, check, and send, then reads off of it from the code field. So when we're actually putting together this function that then gets turned into PyCode, is it called PyCode? Yeah, PyCode. You are using the local builder and global builder to accumulate. So think of it like I passed a list of guards to some context called like, I don't know, build the, because we use the word build too much. I have a context C. I have a bunch of things I pass to it. Its job is to process all of them and turn them into code. And that's what this does. I'll skip over the guarded code.valid. Valid is our invalidation hook for weak ref tensors. I'll like set that whole thing aside for a little bit. But it needs to be prepended to every guard function. So that gets turned into checkfn. So anyway, this produces Python code that is then compiled to check FN. Tensors are different. The entire tensor guard is done through the entire tensor guard is done through C++, and we do it by accumulating tensor names. So tensor check names are a structure somewhat analogous to .code in that it was accumulated by processing guards. But the distinction is that instead of turning to a Python string, it turns into a set of names that is then evaled in C++.
Okay, so rewriting a sec. So I think you've got into the part which you wanted to tell me about at the very beginning. So you're telling me, hey, tensor match is different than conventional guards. And this is exactly what you're saying, right?
Yes,
So
exactly.
the accumulation we do for normal guards is we just jam a bunch of code in, and that's fine
Yes.
and normal. But for tensors, we
Yes.
jam a bunch of tensor names. Let me
Yes.
see if I can guess. Let me guess why we do this. We do this because we don't actually want to generate the code for all the tensor checks because it's like all this random crap like sizes, strides, d-type, etc. Right? So we're gonna like do some other mechanism that lets us save this directly as a structure instead of having to like blat it out in the code. Is that guess right?
Yeah, exactly. It's done for perf and it's done for clarity. And it's done because it's easier to pick which parts to read off the tensor that way. It is also much easier to debug because it's kind of annoying to put debug statements into these giant Python strings.
Yeah.
I actually think all guards should be C++. I think the Python.
Well, yeah. I mean, we need to get there. Do you think we should use like LLVM JIT findings like ArcJIT to do this?
No strong opinion. I think anything is better than a big string you eval.
Okay. Well, I mean, it might not be so great to like have to call GCC to compile a bunch of C++ code every time you want to generate a guard
Well,
because
so
that's
that's
slow.
answering one you don't need to recompile because it sets up those structures. The structure is already determined. It's just like how many of them you have, right? You could do the same thing here. There's only that you just need like a philosophical equivalent to tensor name for like lists, dicts, certain.
Right, right. So you're basically saying let's make a little like interpreter where we
Yeah,
can generate the like byte, but it's not bytecode. Like bytecode is too much of a fancy term for it. It's just like the data structures that.
yeah. There's a small handful of data structures that you can put in C++ and turn those into make the guards just reference those instead of having the big string. And we could always have an escape hash where like we don't know how to C++ this, so it's not worth making. Back to string land we go. Anyway, so that's that's that. But how is it different? Just to tie it back, we said it doesn't make a string the same way. It doesn't go into that big Python string. The mechanism for it not doing so is that it doesn't call produce guard code. Produce guard code is a method invoked 17 times across this file that actually produces this guarded code. You pass it some strings, you pass it some other information, and it makes a code that later goes on those builders, global builder, local builder. Tensor match doesn't do that. It never calls that. And so in my PR, the way this used to look is this was, it had an else here, all this was indented over. And the important bit is that you could get into a state where you have a dot tensor match reference, but the guard is an NN module. So if we look at where tensor match is, there is a.
Yeah, actually, now based on what we talked about, I don't understand how this can happen. Like, what
It's
does
because the
is
source is
NN
NN
module
module.
mean?
It's right here. So source NN module means that the tensor you're talking about has its lineage of the source as a get adder on a tensor module. So
Okay,
like
actually that makes sense. Is this recursive? Like if I get at her, a get at her, a get at her, will it like figure that out or
I think so. I don't remember. I mean, it should, right? It's just a chain of proxies, each is get adder,
okay,
and sources
sure.
can be nested as many deep as you need to. So I
Okay.
think it should be all right. But most importantly is the is NN module source talks about for this tensor from like is it owned by an NN module? Is that how we learned about it? Fundamentally, you can also see this as was this an input? And the answer is no, this was not an input, but we did reference it in some way. So wrap tensor is called from builder when we see a tensor that we don't know about. We need to do some proxying. Before that, we need to create a source for it for internal tracking, for making guards, etc. Then this hint guards are done inside register, adder, or module. That is true. I never
Now
remember where
you
that.
do say that these are not inputs, but like morally they are inputs,
Morally,
right?
there it has to do with the sort of half in, half out nature of functional being like Dynamo isn't functional, so like like local state, is it inputs? If you are AOT autograd, the answer is yes. But if you're Dynamo, the answer is kind of no. But there is like some inputtiness in them. Um, there is a mode that is disabled called Guard NN modules that um, treats all the guards accumulated from NN module associated tensors and other NN module associated values, NN module type IDs, NN module um, just IDs, other properties on NN module, name parameters, register buffers, etc., regardless of whether, like, if they got a guard and they were handled, and config guard NN modules is on, then all those guards would get created. What my PR does is it goes, hold on, before you short circuit this with a continue, check if we care about this specific tensor, even though it came from a guard NN module, because this tensor is associated with a sim shape reference that we care about. So it first makes sure that it's a tensor match, which because there are things that are NN modules but are not tensor matches. The other things I mentioned before. And then this eval, although this eval is a source of sadness, it's actually not it's not special. This eval is the same as calling get. All the guards call .get to get their value in some way or another. And this eval is basically just that. It's saying based on some identifying piece of information and a scope, we don't even need closure bars for it, but based on some identifying information and a scope, give me like the thing. So this is going, am I a guard, am I an NN module tensor? Or is my source an NN module? It is. Am I in a mode that normally guarding NN module properties is disabled? I am. Okay, then check if this came from a tensor. It did. Then check if this ID that we've seen is in the list of tensor IDs that have already been known to be associated with tensor sim shape references. And then if it is, we go, all right, begrudgingly make this guard anyway. Otherwise, we won't know what the heck this thing was. Which, and to tie it all back to what the problem we're solving, which is at certain guards bubble up from sim shapes are not known to us. So what that means is they have sim shapes that ostensibly refer to tensors, but Dynamo goes, I've never seen this tensor before in my life. And the reason it does that is because the source of truth of what it's seen and hasn't seen comes from tensor names. And in order to get this tensor's name to that tensor name list, we have to have this this check right here. And so the reason you're like, well, doesn't this regress perf? I don't think it does, because all you're doing is you're like storing an extra tensor name, and then later you are deciding whether or not you want to keep it and make a guard from it. Well, the thing I was playing with before we hopped on the call is, can we maybe push this check into tensor match and say, and like grab the output graph there, check if this ID for this call get, grab the object, and then check if the ID is in tensor ID to sim shape ref. Yes, we could do that, and then you wouldn't have to have this check here. You would just push it down into tensor match. That is, I think, morally closer to what you like, because you're like aborting the accumulation. You're not waiting until installation time to validate it, but logically, it feels closer to here because this is where we filter away things that are NN modules.
Okay, so I think I understand. Let me check my understanding on a few points. So one is, the reason why config guard NN modules exists is because in the standard case, you're going to have tons and tons of parameters and other random crap on NN modules you access. And you don't want to keep like pinging them for the guards because usually they stay the same all the time. So you're just wasting time revalidating them over and over again. So config guard NN modules is false by default, which means we just skip all that, right?
Correct.
So
yeah, to add a small data point, there was a period where I tried to enable that by default by having it not make guards, but actually watching for module level changes and doing like Python level invalidation using that .valid field, and it still regressed perf. And so I spoke to Ansel, and he's like, forget it. And so we forgot it.
it regressed perf, I guess, because of the valid tests.
I mean, you just like the compile, it didn't not runtime perf, but compile time perf.
Oh, compile time perf. Oh, well, that makes sense because
Yeah,
yes, you're
yeah.
doing a lot of the work.
Yeah, sorry, moving me.
This is my unhappy face. I don't like known unsoundness. We don't have a list of intentionally unsound dynamo behavior, do we? We probably need to start making this doc.
Intentionally unsound dynamo behaviors.
Yeah.
That sounds like a trap.
Well, I mean, Dynamo is intentionally not bothering to check if you mutated NN modules, right?
Um,
And
yeah, I mean, no, I think you're right. Like cheek aside, I think it would be useful to have a list of such features that we call out. There's other places where we fund where we also go like, I hope this is not a bad assumption. Um,
yeah, but this one's a pretty big one because there are things that modify NN modules, and uh, well, you still do check IDs, so that's supposed to catch most of the like module wrapping business.
check
But
IDs, and you also, I think there's things we can do in between the heavy-handed Guard and modules work. Like, I think the answer to that is as you're tracing, if you detect mutations that are like where the source of that, like where the inputs or the source of that call function is an NN module that you would otherwise not guard, you can then go and do like this kind of bypass thing that we're doing here. So I know this is like a fledgling little hack, but I think in the future, maybe it's not like, hey, all NN modules are out. It's more like, is, we talked about promotion of types for guards, and like maybe you just promote things from is NN module to is NN module, but guard anyway.
philosophically, that is a sort of strange thing to do because Dynamo doesn't guarantee that it'll actually understand all of the bytecode, and in particular, it doesn't guarantee that it'll even analyze the piece of code that actually does the mutation.
Well, yes, but then we already do stuff like that with SimShapes, right? Like we check for like comparisons and tuples and all sorts of stuff, and we make SimShape guards. I don't think it would be a stretch to extend that also to accessing an N module.
Right, but with sim shaped guards, like we do like that all happens when we're doing AOT autograd, at which point we know the extent of the
Well,
code we're invoking.
Dynamo has SimShape guards without AOT autograd.
Oh yeah, well I mean that too, but like the sim shaped guards are all about whether or not it's valid to go into the Dynamo track program. That's all I'm saying, right? Like once you escape that scope, the validity doesn't matter anymore. But
That's
with
fair.
a NN module mutation, right, that has implications for unrelated subgraphs in your program.
Yeah. Although I suppose another thing you could say is you could I guess if you really cared about this, you could either enable Garden and modules and just take the compile time hit, or you could ask Dynamo to have another mode analogous to no Python, except what it's doing is it's saying like functional or go home. And then if it sees any state mutations, it just goes no.
Mm-hmm. Okay, let's rewind a sec. So I think I understand why this code works.
Mhm.
One of my questions. Oh, there's a few questions. Where to start? Okay, let's start with a sort of big picture question. So, one question that some of our listeners may be thinking is, man, what the heck is this tensor ID to SimShape ref? And why are tensor match guards related to this thing? And so the answer to this question is that it matters that we create tensor match guards on all inputs because the way that Dynamo dynamic shape tracking is implemented is if you don't guard on a tensor, or well, I think actually you were like making a distinction between guarding on the tensor and putting into tensor names. So let me use the correct distinction. If you don't put a tensor into tensor names, we don't know about it for generating symbolic shapes. And so I was like, wait a second. So my question is, why is this coupled to guards, right? So our like attitude here is something like, we should create a tensor match guard. Well, maybe the confusion is just linguistic, but like when I look at this code, I think to myself, oh, you are trying to make it so that we create a tensor match guard for every input, including the things that come from NN modules, and indirectly by doing this cause the symbolic shapes to be known. But that seems like a very like Rube Goldbergian way to get there. Like, wouldn't it make more sense to just decouple the guarding machinery from the what is the Simmons
Well, this
machinery?
isn't the what is the Simmons machinery. This is more like we already know what the Simmons are. at the cement level, and we already know what the tensors are at the tensor level. Actually, if you look, we're not adding to tensor ID to SimShapeRef. It's already there. This tensor is already there. All we're saying is, hey, hold on, don't throw out that guard.
But why do I care about the guard? Because to put it differently, right? Like the whole reason why we went down this path is because when we were compiling, um, the symbolic shape code, which is completely separate, right? It isn't generated by the normal guard mechanism. It's just this blob that we print out from SymPy.
Yeah.
When we do that, we were failing to find essentially like how to get that variable because we had lost track of it.
Well, we didn't
So
lose track of it. It's more like we see a lot of things in the guard side of SymPy. We see a lot of things in the tensor side of Dynamo, but their intersection is tensors I care about guarding on. And all that this does is when we have a list of tensors we've seen, not all of them make it to the list of tensors we care about guarding on. And this lets one of the ones that normally we don't care about bypass into that list. That's why
but then wouldn't it be sound to just unconditionally put all the tensors into the list of things because it's not a big deal if I don't actually use a tensor on this list
you
to
can't
guard
actually
on.
you could also solve this by just going like this. Like, and now every single thing gets this. The
Yeah,
only
so why don't we do this?
because this is a performance hit because of guarded and modules. For the same thing we mentioned prior, we now have every dot weight, every dot bias, every NN module parameter that is tensor or not going in. So we need another thing, which is like, okay, we could also just write it like.
Well, okay, so rewind a sec. So let me just make sure I understand you. So we
Mhm.
just spent a while talking about guard.create, right? And we
Yes.
said guard.create is guard installation. Is that right? Where we actually do a bunch of string formatting and we accumulate onto local builder. Is that right?
Yes.
So,
Like this would work too. You're basically saying, hey, every tensor that like this check is if I'm not guarding NN modules explicitly through config, but the guard is an NN module and the guard's create function is not a tensor, throw it out. Otherwise, proceed. And this is closer spiritually to what you were saying, where you're like, hey, why not just guard in every single tensor? The answer is we don't need those guards. This extra check is going, well, before you throw it out, make sure that it's one of the ones in tensor ID to SimShapeRef. And that's like a perf thing. We could always just do this and then maybe regress some compile time perf, and you'll get a couple more guards. But this passes because this is less of a constraint than this.
I think mostly what I'm objecting to right now is it seems like there's a coupling between like evaluating our lazily evaluated guard, which happens when we call guard.create,
Mm-hmm.
and just tracking a tensor. Like to me, it seems like I should be able to track a tensor without forcing myself to actually generate the code for a guard.
So this is what I meant by we're not writing to tensor ID SimShapeRef. These tensors are always already tracked. The place where we didn't know about wasn't in general tracking. We didn't know about them in guards. So I could also change the guards to use this for lookup instead of the stricter tensor name table. But I prefer to use the stricter table because then we can know that like this is exactly what this thing is as opposed to this, which is all the tensors we've seen.
Rewind a sec. Let me think. I feel like I would almost prefer that. So let me understand your reasoning. So this is stricter. Why is it stricter? So this is stricter because it only covers the tensors that we allocated symbolic integers for.
Yes.
Whereas how is it stricter? Because it seems to me like whenever I like start tracking a tensor in Dynamo, I have to fakeify it. And whenever I fakeify a tensor, I allocate symbolic shapes for it. So it seems like these should coincide.
Maybe they will. I haven't checked. I imagine that there's cases where we don't go through this registration.
No, but like if so let's suppose we don't go through the registration.
Mhm.
So like I think that's a bug, right? Because if we don't fakeify it, that
Mhm.
means that Dynamo is holding a live tensor, right? And if it at some point realizes it needs to do an operation on it, it can't without actually doing the operation.
Um,
And
Well, there, I mean, there's also like a lazy to fake tensor component to things that is maybe a little bit annoying. But here's a question: like, do backends? Does every tensor that flows through Dynamo to a backend get fake tensorified? Should it?
Yes.
Then this is fine. Then this is equivalent. In fact, if you like, we can also just test it trivially by making it the more permissive check and then adding an assert if it's not found in that table. And then just like, we're done. Then we can also use that to find weird cases where
Yeah,
Dynamo.
cases where we're not converting everything, which we aren't because well, we found that base view thing from symbolic shapes, which I don't think should actually show up in practice, but like is a thing, for example.
Yeah. But either way, it's that check that you have to alleviate, whether you do it in the stricter way or the other way, or whether they're equivalent or not. That's a check that you have to lift. That one that goes, hey, and in module comparisons get thrown out. All the like the guard throw out guards for and modules thing has to get
Yeah.
bypassed.
Yeah. So I think my preference is for the direct check. Maybe that's the refactor you were saying. Like you wanted to push it further. Is that the refactor you were thinking of?
Part of that, yeah. Part of
Yeah.
it was I wasn't going to use the guard tensor match function directly. Instead, I was going to do the check as to I was going to write to the guard instead of adding it to tensor names. But this works too.
Yeah, okay, I see. Yeah. Hmm. Yeah, I just I still think of the guard as generating a piece of code. Yeah, it's just like yeah, the thing where it accumulates tensor names and then we indirectly use them to like figure out the bindings for the symbolic. That's just like so many steps. It's not what I was expecting.
There's a lot of steps.
There's a lot of steps.
But does the fix make sense now?
Yeah, the fix makes sense. I understand why it works.
Okay. I'll remove the
Yeah,
tensor match.
you should mash it into the branch, but like I do want us to keep exploring like more
I think there's a
meaningful
lot
ways.
there's a lot of things we can do to improve guards. I'll land the less permissive or the more permissive one that doesn't have the table lookup, but I'll assert that the ID of it isn't found. So I'll have to keep the eval there.
All right.
Cool.
Well, that's all for today, folks. Thanks for joining us. And yeah, see ya.